Alright, so what we're going to do now is look at the first type of problems that you might see with Beer's law. So basically, again, what we're doing is we are taking the entire electromagnetic spectrum here, and we are focusing it down just on the visible portion of it here. All right, we're just looking at the visible portion because that's where the colorimeters and the spectrometers that we have work in this particular aspect of things. Now, if you did UV, X-rays, or gamma rays, you can get all sorts of other results from those. There's UV spectroscopy, there's X-ray spectroscopy, there's IR spectroscopy, and so forth and so on. But we are not going to be working on those. We are going to be working just on the visible spectrum of light that is here. So here's what a colorimeter actually does. So what you do is you take your source of light here and you put it through a complex series of devices here where it goes into a slit, it disperses, and then again that's basically just a prism, and then it comes out and one of the wavelengths is selected, and we learned how to do that in our previous lesson. We select one of those wavelengths and then we send that wavelength through the sample, and then it comes back through on the other side and it gets detected. Now, basically what it comes down to then is this. Let's say that we have a whole bunch of light that's coming in here, and I'm going to represent it with a bunch of arrows. If you have a colored solution that is designed to absorb some of those things, then not all of that light is going to be able to get through. So some of that light is going to get blocked and absorbed by the particles that are there. So what this device does is it basically measures how much light is going in and how much light is coming back out on the other side, and therefore it figures out how much was actually absorbed from the actual solution. So the more light that is absorbed, the less of it actually goes to the detector over here. So if you have a situation where you have, again, a whole bunch of arrows of light here represented like so, and then only a couple get through, then that's high absorption. But if you have a whole bunch of arrows get through and a whole bunch of arrows come through, then that is going to be low absorption. So the actual absorption is governed by a number of different factors based upon how your device is actually set up here. All right? So we have an equation for it, and it looks like this. A is equal to ABC. Now, what are these things? A here is just the absorption. That's how much light is actually being absorbed by the sample that is being put in the device here. You want to see how much of the light is actually being absorbed by your sample that's there. So that is your absorption factor. And that absorption is dependent upon three different things. The first of which is called A, little a here. And this guy is just a constant. He's just a number that makes things worked out. It's called the extinction coefficient. And the units on that are usually in liters per mole centimeter. And again, don't worry too much about that guy. You'll be given that number. That is just a constant to make all the math work out. Now the other two factors are B and C here. B, I'm not sure why it's B, but anyway, this is the path length. This is how far it is from basically here to here. So that's your B. That's there. That's your path length, and it's usually listed in centimeters. And then finally, C is the important one. That's concentration, and concentration is in molarity. So again, molarity tells us how much stuff is actually dissolved in your sample. So if you have just a few molecules that are dissolved, then your concentration or your molarity might not be so much. That would be a low molarity. But if you have lots of them in there and your solution is extremely dark, then you might have a very high concentration or a high molarity. So that would be a high molarity that's there. That kind of a molarity is going to block more of the light that's coming through. So the light comes in, a high concentration is going to block or absorb more light, and so that less actually gets through on the other side. If, however, you have a low concentration, so again, you have all these arrows coming in and you have a low concentration, then those arrows are going to go through because the molecules are not going to be able to absorb them. So that would be a low absorption. So it's pretty obvious here then that absorption is proportional to this constant, the path length, and the concentration. Let's take a look at some problems. Let's take a look at some problems with this equation. So our equation is just A is equal to ABC. So number one, they're going to give you everything you need here. There's 4 variables in this equation. They're going to have to give you 3 of them. So number one says the concentration of a particular substance is 1 times 10 to the negative 5th, okay? The cell thickness is 2 centimeters, and the extinction coefficient, the constant, is this number here. So basically, guys, they have given you C, that's him. They have given you B, that's him. And they have given you A, that's him. And then it says calculate the absorbance. They want to know that. So this is just that simple. Yes, plug the numbers in. So your absorbance is going to be equal to the extinction coefficient, which is going to be 4 times 10 to the 4th, and that's in liters per mole centimeter, times the path length, which is 2 centimeters, and then times the concentration, which is 1 times 10 to the negative 5th molarity. Please note that you've got a molarity on top and a inverse molarity that's here, so that goes away. And you've got a centimeter on top and a centimeter below, so everything canceled, and you have a unitless absorption number here. And if you plug everything in and do the right math, you end up with an answer here of 0.8 units. And this is one of the few things in science that will actually be a unitless number. The absorption is just 0.8. Number 2 is no different than number 1. The only difference is that instead of asking you for the big A, absorption, they are asking you for the C, the concentration. So, like in any algebraic equation, if there are 4 variables, they pretty much have to give you 3 of them. So they're going to give you the big A, absorption, the little a, the absorptivity constant, and the path length B, and ask you to get C. So the constant is 1.5 inverse molarity centimeters. That was given to you in the problem. The path length, B, is 2 centimeters. And the overall absorbance, A, big A, that is 1.20. So they have now given you 3 of the 4 things that you need. Plug them in and go to town. So the 1.20 is your big A absorption. Your 1.5 is your little a constant. Your 2 is your path length, and there's your x. Plug and chug, and you get an overall value of 0.40 for your x.